Hello calculus fans. Today we start section 11.2, which talks about infinite series. So if you remember, 11.1 talked about infinite sequences, which are lists of numbers written in a definite order. So it's just a bunch of numbers listed out. In this chapter we study infinite series, which are sums that involve infinitely many terms. These play a fundamental role in mathematics, science, and engineering. They're used to approximate trig functions and logarithms, to solve differential equations, to evaluate difficult integrals, to create new functions, and to construct mathematical models of physical systems and physical laws. Infinite series are really important. And the first part of chapter 11, basically, I guess 11.2 through 11.7, just deals with what's called series test to tell whether an infinite series converges, like you can add them all up and get a number, or if it diverges, which means when you add them all up, you get plus or minus infinity, or you get nothing. Like when you add them up, you can't come up with a total. What becomes really important though is after that, once we get past that. So starting in 11.8 and through to 11.11, we talk about what's really important. The main reason we study these is for Taylor series and Maclaurin series, and these are used everywhere. And really in your whole calculus sequence, Calc 1, 2, and 3, Taylor and Maclaurin series are one of the most important things that you'll learn about. And they're very interesting too. You can just do so many different things with them. So that's where we're headed. We just had to get through these series tests first, and we'll start with that with this section 11.2, because it turns out that it's impossible, obviously, to add up infinitely many numbers directly. So we're first going to define what is meant by the sum of an infinite series. As it turns out, unlike finite sums, not all infinite series actually have a sum. So we'll have to need to develop tools for determining which infinite series have sums and which do not. We'll soon see how infinite series are used to evaluate such quantities as sine of 23 degrees, natural log of 5, and how they are used to integrate difficult functions. And that's what I was talking about with Taylor series and Maclaurin series. So first let's recall from the last section, 11.1, we dealt with infinite sequences, which look like this, right? This is the general term and goes from 1 to infinity, or sometimes this isn't shown there. It just looks like this. The general term embraces. And then we have the individual terms, first term, second term, third term, and so forth. Well, if we were to add these terms, okay, then we're going to get something else. So if we were to take these terms and add them, a sub 1 plus a sub 2 plus a sub 3 plus, and on, then what we get is what's called an infinite series. So sequence is a listing. Series is when we add these. Infinite series are just series, and look at the notation we use here. It's a sum. And it makes sense, right? The sum is n goes from 1 to infinity of a sub n. So we'd get a sub 1 plus, because it's a sum, a sub 2 plus, because it's a sum, a sub 3. And we would basically get this right here, going to infinity. So sequence is a listing of numbers. When we add these together, we get series. And remember, sequences are just dealt with in the very first section of chapter 11. All the rest of the sections deal with series, but sequences make an appearance throughout chapter 11, so we just have to know what they are. Okay, so one thing we have to be careful about is when we're working with infinite series, we're going to find the sum of these things. You got an infinite number of numbers. It's a little bit different than if you're dealing with a finite number of numbers. So if you look at this example, 0 equals 0 plus 0 plus 0. Well, 0 is just 1 minus 1, so we put these here. We just rearrange, so we get rid of the parentheses here, and then we just rearrange these terms, and all of a sudden you get 0 equals 1. And there was this guy, Guido Grandi, who came up with this, And this is in the, well, he lived late 1600s to like mid 1700s. And actually, at the end of his proof, he said, therefore, God exists since something has been created out of nothing. Now, some people think that the proof of God's existence needs a little bit more rigor than that. But anyway, it turns out there's something wrong with his proof. We might not know it yet, but we'll see soon. I'll just tell you what's wrong with it, and then we'll see why that is later. The problem with this proof is that this series that he's got, this series diverges. So when you have these listed out like this series right here is a diverging geometric series. So we don't necessarily know what that means yet, but we'll talk about that in this section. So the series diverges. When the series diverges, you can't really make any conclusions about the series. So that was the problem with that proof. But let's look at an example. So example one, we've got this series here. And it's a series because we're adding, right? So we're adding these numbers together. They go forever. We want to find the sum of all of these numbers. Well, to get started, let's think about adding some of them together. We could add the first two, then the first three, and then we'd get a bunch of sums. So if we start adding these up, we get the cumulative sums 1, 3, 6, right? So I add the first one is just 1. Add the first 2, I get 3. Add the first 3, I get 6. And if you keep going, we'll get 10, 15, 21. It just keeps on going, but you can see this doesn't converge to a number. It just keeps on going, so it doesn't converge. It doesn't settle on a number. It doesn't converge to a number because we can see it's just going to make, it's just going to go as large as you want it to go. We can make it go increase forever. So it's said to diverge in this case. Diverge in this case. Another term that we can talk about though is these partial sums. So we could say S sub 1 equals 1, S sub 2 equals 3, S sub 3 equals 6, and these are called partial sums. So when we're talking about convergence, what we do is we're going to look at these partial sums and see if they're approaching a number, if we can predict what they're going to get closer and closer and closer to. Now in this case, you can see they don't approach any number. They just keep growing without bound, which is why we say that in this case, the sum of this series diverges. So let's take a look at this next one. This is a series, right? Because we're adding things together. It's a series. This one's based on Zeno's paradox. Zeno was a philosopher who lived between 490 and 430 BC, and he had a handful of these paradoxes. One of them said this. He basically said, a person cannot walk across the room. So what he would say is this, like, so let's say they've got, let's say there's a room here, and this is one wall, here's another wall, and here's this person. Let's see the person starting right here. And Zeno would say that this person could never touch this wall, because he would say first the person would have to go halfway to the wall to put him here. And then you'd have to go halfway again to the wall. And then halfway again, halfway again, halfway again. And you can continue that indefinitely, an infinite number of times. Now obviously the person does get to the wall. So that was Zeno, the paradox Zeno would say is, what's wrong with my argument? You know, my argument sounds sound. It sounds like you could never get there because you could always go halfway. And when you're real close, you could blow up the distance and look at it and you still go halfway, 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 so you'd never get there. Obviously, we do get there. So how can that be? How can we do an infinite number of things? You can always go halfway again, right? So there's an infinite number of times you're going to go halfway, but how do we actually get to the wall? Well, this is a analytic equivalent of that. Go halfway to the wall. then half of that is a fourth, half of that is an eighth. And if you think about adding these numbers up, and if I just keep adding, so the next one would be 132, right? 132nd, 164th, 1 over 128, and so forth. Couldn't I just make this as large as I want to? I mean, I could add, I'm adding an infinite number of numbers to this list. I'm adding forever. I just keep adding more and more and more. So couldn't I just make this as big as I want? Well, the strange thing is, in this case, if you add all of these up, an infinite number of numbers, the sum of all of these numbers is just 1. And you can see a picture of it. This one's really easy to see with a picture. So just think if I had like a 1 by 1 square, 1 unit by 1 unit. So we know the area of this is 1 square unit. So let's say I want to add up the area, which I know is going to be 1. So I cut it in half. Yeah, it's not really very good half, but let's just say I cut it in half, so that's going to be 1/2. Then I cut that in half, so that's 1/4. Cut that in 1/2, so I cut that in half, so I get 1/8. And cut what's left in half, so I keep cutting these pieces in half. So I know that when I add up all of these numbers, all these little pieces of the area, I have to get 1 because the area is 1. And you can see these numbers here are right here. This is exactly what we're doing right here. We just keep cutting this in half. So cut this in half, so this would be 1/32nd. Cut that in half, so 1/64. We just keep cutting these in half, but ultimately we're trapped, right? The area of this square is exactly 1 square unit. So when we add all these areas together, we could continue indefinitely, an infinite number of times, and we're still trapped in the area of 1. So the note here is what we're doing here is we're adding an infinite number of terms. Right, we're adding an infinite number of terms and getting a finite sum. Infinite number of terms, get a finite sum. Okay, so this is sort of the equivalent of this version of Zeno's paradox. Now, a lot of mathematicians consider Zeno's paradoxes to not be paradoxes anymore because of the idea of a limit. There's other people who don't really accept that definition, and they still think that they are paradoxes. So it sort of depends on who you speak to about it, philosophers or mathematicians. But anyway, this is just sort of an equivalent of one of Zeno's paradoxes. All right, let's take a look at this next example. This example says, find the sum of these fractions here. So we want to see what would happen if we just added all of these up to infinity. Could we make this get as large as we want, like we could in the first example, like in example 1? Or is this more like example 2, the last one, where this has some sum that it won't go beyond? Well, to get a feel for it, let's take a look. So we've got this first term, a sub 1, second term, a sub 2, and a sub 3. And let's take these in the form of a sequence of partial sums. So we're going to form a sequence, right? A sequence of these partial sums. So what we could do is this. We could say S sub 1, the very first sum is 1/2. That's just by adding, starting with the first term. S sub 2 is going to be the first 2 terms added together. Okay, so S sub 2 is going to be 1/2 plus 1/6, which ends up being 2/3. So we got 1/2 for the first term. Add up the first 2 terms, and we'll get S sub 2, which is 2/3. Now S sub 3 would be the sum of the first 3 terms, which is 1/2 plus 1/6 plus 1/12. And when you get common denominators and add all those together and simplify, you get 3/4. Okay, and if we kept going along this route, we'd be able to see a pattern. So we can say etc. So what we're looking for, here's our question. The question is this: what is s at infinity if we add up an infinite number of these terms? So in other words, if we could possibly add up all of the terms going to infinity, what would we get? I don't know, what would that answer be if we could add them all up? So what we're going to do is see if we can use the idea of a limit to find that. All right, so we have a sequence. So let's look at what we've got. So we have the sequence. Remember, a sequence is just a listing of numbers in a definite order. So we're back to sequence, and the notation would look like this. Remember, notation of a sequence, we have these little braces, S sub n. That's the notation of the sequence. So here's our sequence. We have 1/2, 2/3, 3/4. Basically, this is a sequence of these partial sums, right? S sub 1, S sub 2, S sub 3. Now, if we kept on going, we would get 4/5, and we could keep going. We could see a pattern here, n over n plus 1, and we could keep on going. So what this is, okay, this is a sequence. It's a sequence, a listing of numbers. It's a sequence of partial sums. Okay, so here's the important part. Here's what we're thinking. When we added the first term together, we got this. Added the first 2 terms, first 3 terms, first 4 terms. So what we want to see is, what if we added the first 1,000,000 terms? And what about 1,000,000,000 terms and 1,000,000,000,000 terms? Does it look like these numbers are approaching something? Right, that's what we're looking for. Like, can we see a pattern in all of these partial sums so that we can use the idea of a limit to find this actual sum at infinity? Well, it turns out we can, because we can find a pattern. See, this is like n over n plus 1, right? S sub 1, there's a 1 up here. S sub 2, there's a 2 up here. S sub 3, there's a 3 up here. The denominator is just 1 more. So this is the pattern. So what we can do is we can take the limit of S sub n, right? So it looks like S sub n is this, because we've got, so for instance, S sub 2, if I use this, it's going to be 2 over 3. Sure enough, S sub 2 is 2 over 3. So in this particular case, we can find a pattern for the nth term of this sequence of partial sums, right? We can find a pattern for it. Can't always do it, but we can here. So since we can, we want to take the limit of this as n approaches infinity and see what that would be. So here we go. Every time you guys think we're done with limits, they make an appearance again. So this will remind us of the good old days in Calc 1, when we're using limits and we would take the limit, we get infinity over infinity. And eventually you usually learn about L'Hopital's rule. But before that, you would learn a technique that would say basically divide each of these by the highest power in the denominator, which in this case would be n to the first power. And the way you show that algebraically is you do something like this. You multiply by 1 in the form of 1 over n over 1 over n, which essentially is divided by the highest power in the denominator. So I multiply across here, I get 1 on top. When I multiply across here, I distribute, and I'll get 1 plus 1 over n. So this gives us the limit as n approaches infinity of 1 over 1 plus 1 over n. Of course, we can take the limit of this as n approaches infinity, 1 over n. This becomes as close to 0 as we want. So we could make it completely insignificant. We could make it so small that it doesn't really matter. So the limiting value of this, the limiting value is exactly 1. Meaning, by making n large enough, we can make this as close to 1 as we want to. And it turns out that this 1 is the sum of the original series. The original series, right? The original series is the sum of this series up here. If you were to add these all together, it looks like we would just get 1. Now they don't all add up to 1, just in case you're wondering. They don't. They could add up to anything, really. We just had a couple that add up to 1. So it's like a limit again, right? Like we could go far enough so that we could make the sum of this series be as close to 1 as we want. That's what we mean here. The sum of the original series is 1. Then the note here is the sum of a series is the limit of the sequence of partial sums. So if you can find a formula for the sequence of partial sums, you can just take the limit of that. Now we'll find that normally you can't find this. Normally it either doesn't exist or it's too complicated, too difficult to find. But when you can find it, it's really nice. We can just take this, take the limit of the sequence of partial sums, and that ends up being the sum of the series. And that brings us to a box, which means something important's happening, right? You get a definition. Let a sub 1 plus a sub 2 plus a sub 3, and so on and so forth, be an infinite series. It's a series because we're adding the numbers together, right? A sequence is just a list of numbers written in a definite order, but a series is only adding these together. So this is an infinite series with s sub n the nth term of its sequence of partial sums. Right, just like before, this is a partial sum, the nth term of its sequence of partial sums. If the sequence of partial sums is convergent, meaning it converges on a number, we can make it as close to a particular number as we want. And then the limit is then approaches infinity of s sub n equals s, which is an element of the real number system. All this says right here is this s has to be a real number. S is an element of the real number system. This script R a lot of times is used to signify the real number system, which basically is all the numbers we use other than the imaginary numbers, right? Square root of negative 1 is not in there, but everything, all the real numbers we've been using all throughout calculus. As long as it's one of those and it's not infinity or something like that, then this series, a sub n, so we've got a series here, right? Sequence, remember the notation for a sequence, a listing of numbers, we're listing out those partial sums. Then the original series is convergent and its sum is s. Otherwise, the series is divergent. So if we take the limit and we don't get a number, maybe we get plus or minus infinity, or we just get a limit that doesn't exist. In that case, we would say the series is divergent. And we say its sum is s. Remember, that's like the limiting value, meaning we can make it as close to this number s as we want to. There's a special infinite series called a geometric series. And this is one in which there's a constant ratio between any two consecutive terms. Let's say ratio r. Okay, ratio r between any two consecutive terms. Okay, so you can see by looking at this, to get from 3 to 6, I doubled it. I multiplied it by 2. I multiplied 6 by 2, multiplied this by 2. So the ratio is 2. Sometimes they're not really easy to find this way, so you can find them just by taking a term and dividing it by its previous term. Right, so 12 divided by 6, well, that's 2. 6 divided by 3, that's 2. And it will work for any of them. If it's a geometric series, that ratio will be constant. So you can pick any term, divide it by the previous term, and you'll get the ratio r. So in this case, this one, I guess, is easiest if you just take the first two terms. And if I take negative 2 and divide it by 3, well, I get r equals negative 2/3. But just to show you, it doesn't matter which ones you do. So I'm just going to pick these two, right? So I'm going to say, all right, I'm going to take negative 8/9 and divide it by 4/3. We know when we divide fractions, what we're really going to do is multiply by the reciprocal, right? We don't ever divide here. What we're going to do instead is multiply by the reciprocal, which would be 3/4. Okay, then we can see we've got some canceling that will happen. 3 goes in here once, 3 goes in here 3 times, 4 goes in here once, goes in here 2 times. And then when you multiply straight across, you get negative 2/3 or negative 2/3. Okay. And then this one, what's this one going to be? Well, if you take this term divided by that term, you get negative 1 over 1, which is just negative 1. So here the ratio r is negative 1. So it turns out for geometric series, we're going to actually have a formula for the sum of the series. This is really unusual. What we'll see pretty much when we get done with section 11.2 is that most of the times we'll only be able to tell whether or not a series converges, but we won't typically know what it converges to. But geometric series is one of the few that we can actually tell what it converges to. So to figure that out, we need to take a look at this. So this is the geometric series. You have a times r to the n minus 1. R again is a ratio. So as n goes from 1 to infinity, if you were to list out the terms of the series, it would look like this. If you were to expand the series, right, not use the summation notation, but just go right through here, plug in a 1 and then a 2, and you'll see you get here. Because the first term, when you let n be 1, you get a times r to the 1 minus 1. It's a times r to the 0. Out of the 0 is just 1, so you just get a. Right, then you plug a 2 in here, and you'll get here, and then a 3, and a 4, and so forth. There's a little note here, s sub n. So the sum of the first n terms of the series, there's a formula here. It's a plus a to the r plus a, or a times r, plus a times r squared, and so forth. You notice what this n, and then there's n minus 1, which makes sense if you think about it. Like, let's say we're going to take the first 3 terms. If this were s sub 3, we'd have this one plus this one plus this one, and r would be squared, right? So it's just going to be, when you list out s sub n, you end up getting this. So what we want to do, because we're going to come up with a formula that will allow us to figure out the sum of the geometric series, we're going to need to tweak this a little bit. So if we were to start with s sub n, and then multiply, so I'm going to actually start with this equation. I want to multiply each side of this equation, so the left side and the right side. I'm going to multiply them both by r. Okay, so just imagine we multiply this by r, and then multiply this whole thing by r. Right, so this r would distribute through here all the way down. So what we would get then, we would have r times s sub n equals, so we have a times r plus a times r squared. Basically, just all of these terms are getting multiplied by r, right? a times r squared. And we go all the way down here, so we'd get plus ar cubed plus ar to the 4th plus. Now think about this term, the term in this list previous to this one would be ar to the n minus 2. So this r comes through there, and that turns into ar to the n minus 1. So we have plus ar to the n minus 1. And then finally this last term here, when I multiply this by r, I have ar to the n minus 1 times r to the 1. So we add those terms, and the minus 1 and the 1 will cancel. So that would give us plus a times r to the n. Okay, so what we're going to do from here, and again, the whole reason we're doing this is to develop a formula, because you know what happened. If I just put that formula in a box and said, here's the formula, you'd be like, no, wait a minute, Kurt, wait a minute. Sure would like it if you could explain that formula and where it came from. Okay, so that's why we're doing this, to get a little bit ahead of the game here. What I'm going to do is you want to take this original s sub n, we want to subtract r times s sub n. Okay, so let me, just to make it easier, let me erase this stuff up here. Okay, so what we want to do is we want to go s sub n minus r times s sub n. So we're basically going to subtract here, and then we're going to take this and subtract all of these. We're basically taking this equation and subtracting this equation. So when we do that, we would get s sub n minus r times s sub n equals, and I'm going to take this and subtract all of these. So you can see a bunch of these are going to cancel. When I subtract those will cancel, those will cancel, those will cancel, and this would cancel, and that would cancel. Basically, everything in here would cancel, and the only thing we'd be left with is this term and that term. So over here we'd have A minus A times R to the nth power. Okay, so next thing we want to do is factor a little bit. So I'm going to, on the left side of the equal sign, I'm going to factor out S sub n, and I'll get 1 minus R. On the right, I'll factor out an A and get 1 minus R to the n power. Then we want to solve this for S sub n. So basically, I'm going to get this by itself. I'm going to divide each side by 1 minus R. So I get S sub n equals A times 1 minus R to the n over 1 minus R. And sometimes you'll see it written this way. Sometimes you'll see it's essentially multiply that fraction by negative 1 over negative 1. You get A times R to the n minus 1 over R minus 1. This one's just a little easier to use when R is greater than 1. Now, in pre-calc, some of you probably learned about finite series in pre-calc, and you may have seen something like this, but here's where you would stop in pre-calc. It used to be taught all the time in pre-calc. It's not taught that much anymore, so most students now, when they're in calculus, they haven't worked with finite series. It's okay. I'll just mention this in case if you did happen to cover that topic in like a pre-calc or maybe an algebra class, you would have seen something like this, but you would stop here. But in calculus, what we do, we go one more step. Because in calculus, what we do is we take the limit of this thing as n approaches infinity, which is the limit of this as n approaches infinity. Okay, so we're going to do the extra step in calculus. So here's where calculus comes in. We take the limit as n approaches infinity of S sub n, the nth partial sum. That gives us the limit as n approaches infinity of A times 1 minus R to the n over 1 minus R. And now we have to think about what would happen here. So R raised to the nth power. Think if R were 1/2. Okay, I'm just going to write this down on a little scrap paper here, or a little piece here. So think if R were 1/2, and so we have 1/2 to the nth power, and n is going to infinity. So as n gets huge, well, the numerator is just going to be 1, right? I mean, you could think of this as being 1 over n and 2 over n. Well, 1 is just going to be 1, but this is going to be 2 over n. So n gets huge, the denominator gets huge, and you have 1 over a giant number, which will eventually go to, the limit of which would be 0, right? We could make this be as small as we want just by letting n get big enough. So if we had a number like that, like 1/2, or basically a number less than 1, it would work for any number less than 1, right? If you raise the number less than 1 to a power, it gets smaller. So this thing would go to 0. If R were less than 1 and I take the limit, this goes to 0, so all I have left on top is A, right? So in this case, we would get A over 1 minus R. We would get that if, this would be if the absolute value of R is less than 1, which implies that negative 1 would be less than R, which would be less than 1. You may remember from algebra class writing the equivalent. If you have this with absolute value, it's equivalent to this, right? You could think of it as like the distance between the origin and R, some number is less than 1, which means that that number R is between negative 1 and 1, right? So when R is small, a small number, absolute value less than 1, take the limit, this goes away, so you just get this. Okay, so that actually means it converges. If we get a number, it converges. So if the absolute value of R is less than 1, the geometric series converges. But let's just, let me move this up a little. Let's say, on the other hand, what if R were like a 3? So it's a number bigger than 1. Well, if I put a 3 in here and have 3 to the nth power, Well, as n gets bigger and bigger and bigger, I just have this giant number here, and there's a negative in front of it. So basically, it'd just be a negative number here, right? And it'd be over here, too. If I have like 1 minus 3, which would be negative here. But you can see I'm going to get an infinity, right? There's going to be an infinity involved here. So if this isn't the case, we're going to get, well, it could be a couple of things. If r were greater than or equal to 1, we're going to get infinity. But if r is less than or equal to a negative 1, then we get some weird case where, say, the even terms are going towards infinity, the odd terms are going towards negative infinity. But in either case, it doesn't exist. Okay, so the other thing that could happen is we could take this limit and we get a couple of things. We could get plus or minus infinity, or we could get a limit that does not exist. Okay, but in either case, it doesn't matter. They both diverge. And this happens if the absolute value of r, let me rewrite that. If the absolute value of r is greater than or equal to 1, which means r is greater than or equal to 1, or r is less than or equal to negative 1. And again, I'm just rewriting this the way you can always rewrite an absolute value, which you probably learned in an algebra class in the past. So for a geometric series to converge, we need the absolute value of r to be less than 1. And if it converges, we can calculate what it converges to. So in summary, we've got a little box here. If we have a geometric series, well, it is convergent if the absolute value of r is less than 1. It converges. In other words, if r is between negative 1 and 1. And we know its sum, right? We actually have its sum, which is nice. And let me point out this a. This a is the first term in the series. So a is just the first term in the series. Okay. On the other hand, if the absolute value of r is greater than or equal to 1, which means r is greater than or equal to 1, or r is less than or equal to negative 1, then the series diverges. And if it diverges, there's nothing else to do. We just say it diverges. The series that we're going to be more interested in are the ones that converge. So if it converges, we can actually find the sum. If it diverges, we just say it diverges, and we're kind of done with it. Okay. And so this is, again, this when we say sum, we're saying the limiting value, right? We could make this series, we could make the sum of the series be as close to this number as we want to just by going far enough out. So we say it's the sum. What we really mean is the limiting value. Now I know you guys, as soon as you see a box, you're like just itching to try some of these. And here we go. You have to actually add another one of these, but let's take a look at these. So example 4 says, determine whether the following series are convergent or divergent. If they're convergent, find the sum. So these are geometric series, so we just want to see if they're convergent or divergent. So what we basically have to do is find r for all of these. So to find r for this series, I just need to take any one of these terms and divide it by the previous term. So I'm just going to take these first two. So I'm going to take 1/6 divided by 1/8. 1/6 divided by 1/8. Of course, that's the same as 1/6 times 8 over 1, which is 8 over 6, or 4 over 3. So r is basically 4 over 3. So we know this is a geometric series. Well, it's geometric series because if I took any of these and divided by the previous one, I get 4/3. Or if I start here and multiply by 4/3, I get here. Then multiply this by 4/3, I get here. Multiply this by 4/3, you get here. Okay, so it's a geometric series with r equal to 4 over 3, right? R equals 4 over 3. Therefore, the series diverges. The series diverges. Remember, this little symbol here just means therefore. I know it diverges because r equals 4/3, right? Which means r is greater than 1. The absolute value of r is greater than 1. When that happens, greater than or equal to 1, sorry. When the absolute value of r is greater than or equal to 1, we know the series diverges. All right, now this one may look familiar. We've seen this one before. So if you were to go ahead and look at it, you'd see that, well, this is a geometric series with r equal to 1/2, right? Because you could take any one of these terms divided by the previous one, you'll get 1/2, or alternately, you could take the first term, multiply by 1/2 to get here, and you keep multiplying by 1/2. Okay, so the ratio r is 1/2, which converges because r in this case, the absolute value of r is less than 1. So this series converges, right? So this converges, and we can find its sum. So the sum of this series, sum equals, sometimes people like a little s infinity, but the sum equals a over 1 minus r. Okay, remember a is the first term in the series, so you look over here, the first term is 1/2. 1/2 over 1 minus r. Well, r is also 1/2, right? R equals 1/2. So you plug this in and do the arithmetic, we get 1/2 over 1/2, which of course is 1. We already knew that it converged to 1 because we did that little example of the 1 by 1 square. Okay, so I want us to squeeze one in here. Let's squeeze in b and 1/2. And b and 1/2 looks like this. They give us in this form here, it says n equals 1 to infinity, 10 to the n, over negative 9 to the n minus 1. Okay, I want to make sure we can handle this kind too. Okay, so what we want to do is get these to be the same power. This is to the nth power, this is nth minus 1 power. Okay, but we do know something from algebra and from oh my gosh, I can't speak. From algebra and using rules of exponents, that I could do this, right? Couldn't I just take 10, peel a 10 off of there and get this? Right, because this would be like 10 to the 1 power. So I multiply these together, I'd have to add the power, so I get 1 plus n minus 1, which would just be n. So I'm basically just peeling a 10 off so that these will be to the same power. And this 10 is just a constant, so I could even move it out front here if I wanted to. I could move it in front of this symbol, in front of the summation symbol. This gives us 10 times the summation as n goes from 1 to infinity of 10 to the n minus 1 over negative 9 to the n minus 1. Now, since these are the same, make a little divider here. Okay, since these have the same power, we can combine them into one fraction. So we can say this is equal to 10, and then n equals 1 to infinity, and we have 10 over negative 9 to the n minus 1. Now, as soon as we get there, we are okay. We can see that r is negative 10 over 9, right? R is negative 10 over 9. The absolute value of r is 10 over 9, which is greater than 1. So we know this series diverges. The series diverges because the absolute value of r is greater than 1. Okay, so I just wanted us to slide that one in there so we could see something a little bit different. And then this last one. So this one, you should just try this one. See what you come up with. Right, meaning press pause and try it. Don't just sit there looking at the screen waiting. Right, press pause, try it out, and then check back. Right, so hopefully you found r. So I'm just going to take this term and then divide by this term. So I'm going to have this divided by this. And of course we know that that is equal to this times the reciprocal of the square root of 3 over 1, which would be 1 over the square root of 3. And then, of course, this, we know we can write these under their own radical, right? So that's really the same as square root of 3 over the square root of 2 times 1 over the square root of 3. and then these square roots will cancel. So you end up with 1 over the square root of 2, and this is what r is equal to. So 1 over the square root of 2 is roughly 0.7. So that tells us that this converges, because we know it converges if this is true, right? And that's what we've got. So we know this converges. So it converges to a over 1 minus r. A is the first term in the series, which is the square root of 3. So it converges to, let's see, so this is equal to the square root of 3 over 1 minus r, which is 1 over the square root of 2. All right, let me ask you a question. Would you ever hang out with somebody who left their answer like this? I doubt it. I'm pretty sure you wouldn't, right? You have standards for your friends? This is just not a good answer. We don't want to have fractions inside fractions, have these complex or compound fractions, so we want to fix it. We can fix it easy enough by multiplying by 1 in the form of the square root of 2 over the square root of 2. So if we multiply here in the numerator, we're going to get the square root of 6, right? So we get the square root of 6 in the numerator. In the denominator, we're going to have to distribute. So the square root of 2 times 1 is the square root of 2. And then the square root of 2 times 1 over the square root of 2 with a negative is just going to be minus 1. Okay, so this series converges to this number right here, meaning we can get this, if we go far enough, we can get it as close to this as we want. And we can interpret that as if we added up all the infinity of terms here, we would get exactly this. Okay, so hopefully that one made sense. And now we've got another kind of problem. We want to find the fraction represented by this repeating decimal. Now I'm just going to give you a quick, easy one that you may have seen before. You may have seen this, sometimes people will say 0.9 repeating equals 1. And it's a matter of limits. So it means basically we can make this as close to 1 as we want. So the limiting value of this is the same as 1. And the way they'll do that is they'll say something like, okay, let's let n equal 0.9 repeating, which should then be 0.9999, right, forever. So then 10n, if I multiply that by 10, I get 9.9999 forever. Then you can do a little problem, say, okay, so 10n equals this, n equals this, and then we subtract 10n minus n, well, that's 10n minus 1n, that's going to be 9n, and we subtract this, all this cancels except for 9, which means n equals 1. Okay, so you may have seen an argument like that, but what we're going to do is do something like this. So you're going to use algebra, do something like this to figure out what this one is. Okay, so let's get this out of here a second and start fresh. Okay, so we can do something like what we just did. So what I'm going to say is let's let n equal the original number, 4.1, and then there's a bunch of repeats, right? 3, 6, 3, 6, 3, 6, on and on. Well, what we need to do is we need to get to this repeating part. So I need to get this decimal over here to the 0.363636 that repeats. So I'm going to multiply this number by 10. So I need to multiply n by 10. So we could say, okay, so if n is that, then 10n is 41.363636. So at this point, we've got one equation that sort of, you could think of as like isolating the repeating part, but we're going to need two, and this one doesn't quite do it. So I'm going to also move this over 2 more times. So it'd be like 10 times 100, right? So it'd be 1,000n. So let's figure out what 1,000n is. 1,000n, well, if n is this, 1,000n will move this over 3 times. So you get 1, 2, 3. So it's 4,136 point, and then all the 3 sixes repeat. So then what I'm going to do is something similar to what we did before. I'll take the 1,000n, which is 4136.363636, and I'll also take the 10n, which equals 41.363636. Oh, I keep forgetting some of these ellipses here because these go on forever. Then we're going to subtract. We're going to subtract each side. Right, so then that gives 990n equals, we subtract here, we get 4,095, and then of course all of these just go away, right? So if you divide each side by 990, you get n equals 4095 over 990, and that actually simplifies to 91 over 22. So if you want to check it out, if you punch this into your calculator, 91 over 22, and if it's in decimal mode, you're going to get this number. Okay, so that's how we can do this problem using algebra. But I know you guys do not like using algebra because you are in calculus. So you're going to want to use calculus. Okay, we can do that too. This particular problem, the algebra is a little bit easier, but we can use calculus and in particular geometric series to do the same thing. So I'm just going to write down the original number. Okay, we have 4.1363636 forever. Well, we know that's really equal to 4 plus 0.1 plus 0.036 plus 0.00036 plus ... Right, because if you add these up, this would be 4.1, and then 0.036 gets us here, and then you put this one, which will get us here, and it just keeps on going. Then let's write these as fractions so that it'll be easier for us to work with in a second here. Okay, so this is going to be 36 over 1,000. This is going to be 36 over 100,000. And then this right here, this is beginning of a geometric series. This is all a geometric series because basically I can multiply this by a number to get here, multiply this by the same number to get to the next step, the next step, the next step. Okay, so to find the number, first let's just notice that this is a geometric series. And R is equal to, well, I'm going to take 36 over 100,000 and divide it by the previous term, 36 over 1,000. Okay, so to do that, what we could do is, instead of dividing, of course, we could just multiply by the reciprocal. This is 36 over 100,000 times 1,000 over 36. Okay, the 36s will divide out, and 1,000 will completely go. Take 3 of those with it. So we're really left with 1 over 100. So R is equal to 1 over 100. Now, you may have been able to see that just by looking. If I multiply this by 1 over 100, I get here, because basically I have 2 more zeros in the denominator. Okay, so let's geometric series with R equals 1 over 100. Well, 1 over 100... that's less than 1, right? Which means this converges. So let's see what we have then. That means that 4.1363636 is going to be equal to 4 plus 1/10. And now what we'll do is we'll use our formula. We'll use this formula A over 1 minus R, and we'll start right here. This will be the first term, right? So we're going to add this to this series. So A, this is our first term, so we'll have plus 36 over 1,000 over 1 minus r, and r is 100. Okay, so that is going to be 4 plus 1/10. Okay, so down here, this is the same as 100 over 100, right? If I rewrite 1 as 100 over 100 minus 1 over 100, that would be 99 over 100. So that would be plus 36 over 1,000. And then this would be 99 over 100, right? Again, this is 100 over 100 minus 1 over 100. And then, it's, of course, instead of dividing, we'll multiply by the reciprocal. So maybe I'll just do this off to the side here. So 36 over 1,000 times 100 over 99. All right, so 100 is gone. It'd leave us with 2, or with 2 zeros would be gone, so leave us with 10. So we'll get 36. You multiply across, we get 36 on the top, we get 990 on the bottom. And let's see, that actually reduces to 2 over 55 if you divide everything by 18. Okay, so this means you've got 4 plus 1/10 plus 2 over 55. And if you, I just use my calculator for this one, add those together and write it as a fraction, you get 91 over 22, which is what we got last time. Okay, so again, the algebra is a little bit quicker in this case, but just to show that we can use a geometric series also here, so we get the same answer. Okay, you guys realize you're getting your money's worth with this section? 11.2 is a big section, so you're getting your money's worth. We're coming up on an hour and still going strong. Still have some more to go. So hopefully your caffeine reserves were good before this video and you're still hanging in there. So this series here we saw earlier, and this we know converges to 1. That was the, we looked at that one earlier in the video. So now we're going to consider another series. So this series, 1 over n. This sum from n equals 1 to infinity of 1 over n. And if you list out the first few terms, it goes like this. This is a very famous series. This is called the harmonic series. This series, it turns out, diverges. This series has a long history and it's related to music. So there's a lot of overlap here with a series like this and music. And if you, you know, later on when you're done with your homework, maybe take a look at that online. And especially if there's any musicians in this class, you'll definitely appreciate it. But this harmonic series, it diverges. It was first proven to diverge in the 14th century, and that proof was lost to history and was found later, hundreds of years later. But there have been later proofs in the 17th century. There's kind of an easy one though you can use to show that it diverges. So I'll show you just a real easy one. So let's say we've got this series here, 1 over n, and I'm just going to list it out. I'm going to write out a few terms here. You have to go to 1 over 8. That's how far I have to go to make this proof seem right. Okay, so we'll go here, and I just want you to notice something about this. Okay, so this 1/3 plus 1/4, that's more than 1/4 plus 1/4, right? Because 1/3 is bigger than 1/4. Okay, and then look at the next set of numbers here. These 4 are going to be bigger than 1/8 plus 1/8 plus 1/8 plus 1/8, because these numbers here are all bigger than 1/8. And then if we were to continue this process, we'd go all the way to 1/16, and we do something very similar here. But what you can notice is then since this is equal to this, right, and this up here is greater than this, then we can say this. So this summation from 1 to n is greater than 1 plus 1/2 plus, well, this is 1/2. This is another 1/2, so we can add those. And basically the argument is we can make all of these next groups be greater than 1/2. So we're just adding 1/2. And there's no way this is converge if we keep adding 1/2. We're not adding smaller and smaller and smaller numbers. We're just adding 1/2 forever. So that means that this diverges. And if this diverges, well, then this must also diverge since it's even bigger. Right? So we're adding these up, and it's going to infinity. And this one is even bigger than that one. So this one definitely is going to go to infinity too. So this is the basis of an argument that was used as a proof. But the harmonic series, the takeaway is this harmonic series that looks like this, even though these get smaller and smaller, they don't get smaller and smaller fast enough. So this you can make be as big as you want. It may take a while, but if you added long enough, this would go, the series, the sum of the series would go past 1,000,000 or 1,000,000,000 or 1,000,000,000,000 or whatever number you pick. If you add long enough, it'll go past that. Okay, it is time for a theorem. We've got a theorem here that says if the series listed here converges, then the limit of a sub n has to be 0. Now this totally makes sense if you think about it. If this series is going to converge, that means we can make these terms we can make the sum of these terms get closer and closer and closer to a number. So the only way that's going to be possible is if these numbers get smaller and smaller and smaller, right? We can't just keep adding 10 and think it's going to zero in on a number. For this sum of all these to zero in on a number, these have to get smaller and smaller and smaller. So it just basically says if this series converges, then the limit of a sub n, the limit of these terms, this a sub n has to be 0. It's got to get smaller and smaller and smaller. Okay, so it kind of makes sense. But we have to be careful of this one because the converse is not true. So in other words, I can't just say, well, since these terms are getting smaller and smaller and smaller, and the limit is 0, then it converges. An example of that is a harmonic series. Okay, the counterexample would be the series we just looked at, the harmonic series. If you look at the harmonic series, a sub n there is 1 over n. And the limit as n approaches infinity of 1 over n is definitely 0. But it's not enough. Just saying the limit is 0 doesn't guarantee that the series will converge. Okay, but we do know if the series does converge, then the limit of this nth term will be 0. And it turns out that we can use this for our first convergence test. We can use that theorem. Now this test goes by many names. The test for divergence, the divergence test, and sometimes it has another term, I'll just say the nth term test. The nth term test. All of these refer to the same thing. And basically all it says is this. If the limit of the nth term of a series does not exist, or the limit is not equal to 0, then the series diverges. Okay, so it does not exist. I'll tell you what it normally means. Normally does not exist means it's going towards plus or minus infinity. But it could also, maybe you take the limit and you come up with something that just oscillates indefinitely without ever approaching any one number. That would also qualify. But usually you'll get a plus or minus infinity, but you could get like a number like 1 or 7. Basically, if this thing is not going towards 0, it definitely cannot converge. So if the limit is not approaching infinity, if the nth term is not 0, the series diverges. Okay, so there's good and bad about this test. The good about the test is it's super easy to use. You can use it really easily. Just take the limit of this nth term. And if you don't get a 0, you're done. And you know the series diverges. The bad, I guess, the pros and cons, the con to the test, is that usually when you use this test, you get 0. And if you get 0, the test then gives us no information. So this is important. Okay, so let's say you use this test, and you take the limit as n approaches infinity of a sub n, and you get 0. Okay, when that happens, the test fails to give us any information. That means the series may converge or diverge. The test just fails to give us any information, so we need to use a different test. Use another test when this happens. So that's the con. The pro is very easy to use the test. The con is it often fails to give us information. Often when we take the limit that approaches infinity, we just get 0. Okay, but when we do get a number that's not 0, it's really fast and really nice to use. Okay, but anyway, that is our first test. So let's try it out here on this next one. So example 6 is determine whether the series listed here is convergent or divergent. Now notice this series is in terms of k. Most calculus resources will use n here, but some use k. So we have to be ready to see k also. It really could be anything, but n is the most common and k is probably the second most common. But we can use the test for divergence. Let's just take the limit of this. Just take the limit of the nth term. So we could say the limit as k approaches infinity of k over k plus 1. Well, this is something we would have seen in Calc 1, right? We have infinity over infinity, indeterminate form. Right, in Calc 1, the two we saw all the time were 0 over 0 and infinity over infinity. 0 over 0 has a few different techniques to get through, but infinity over infinity has like a go-to method. Divide by the highest power in the denominator, right? Or you could use L'Hopital's rule for both of these too. But let's stick to the original way. Divide by basically k, divide everything by k, which we could do algebraically by multiplying by 1 in the form of 1 over k over 1 over k. So if we do this, we'll get the limit as k approaches infinity. Numerator will be 1, and then we'll get 1 plus 1 over k. We can take the limit, and this term goes to 0. Right? We could make this term as close to 0 as we want. The limiting value of that would be 0. And that would just give us 1, which is not equal to 0. Right? So that means the series diverges. So the series diverges by the test for divergence, or by the divergence test, or by the nth term test. Now most of these tests just have one name. This is just kind of unusual. It's got 3 different names. Okay, so that brings us to, we're getting close now. We're getting close. Example 7. When you look at this one, it's a little different looking. But let's just try the test for divergence. Okay, let's just try it out and see what happens. All right, so if I want to try the test for divergence, I could take the limit of this as n approaches infinity. So I'll just mention this. Let's try the divergence test. Try the divergence test. Okay, so we take the limit as n approaches infinity of 1 over n plus 2 times n plus 3. You can see what's going to happen. This denominator is going to get bigger and bigger. Numerator stuck at 1, so the whole thing is going to go to 0. Goes to 0, what does that mean? Well, it means nothing to us, right? It means that divergence test failed to give us any information. Had we gotten a number other than 0, like some other number, then we'd be done already. But we got a 0. So when we get a 0 with a divergence test, it just means it gave us no information. We need to do a different test. Okay, so it didn't work, but we've got something else we can try. In fact, let's try using partial fractions to break this thing up. This is going to be another sort of famous sort of series. You can see it coming when you start to think, well, maybe I could use partial fractions. Okay, so let's use partial fractions. So we tried the divergence test. It didn't give us any information. So let's use partial fractions. Try something else. Okay, so we've got, let's see, 1 over n plus 2 times n plus 3 equals a over n plus 2 plus b over n plus 3. And the way that I will do this one, I'm just going to multiply each side by the denominator. If you remember from doing these before, when we do this, we'll basically multiply this side by n plus 2 times n plus 3 and also this side. So what will happen is this side, it will cancel everything but the numerator. So I have 1 equals. And over here we're going to have a times n plus 3 because the n plus 2 term will get canceled here. And then we'll have plus b times n plus 2 because the n plus 3 term will get canceled with this. Okay, and then we just pick some easy numbers. So let's say I'm going to let n equal -3. Then I get 1 equals, well, that will wipe this term out. So I'll get -3 plus 2, which is -1. So I'll get negative b. That implies that b equals -1. Okay, and then let's go n equals -2, and we'll get 1 equals a times 1 plus b times 0, which means, okay, a equals 1. Okay, so what we've got then is this series that, sometimes the software does what it wants to do. Okay, let's see if it will cooperate this time. This series, n equals 1 to infinity, of 1 over n plus 2 times n plus 3. Okay, this is equal to, so I'm going to move it down a little bit here, but it's going to be, a we said was 1, so that's going to be n equals 1 to infinity, 1 over n plus 2, and then b we said is -1, so it'll be -1 over n plus 3. Okay, so these are the same. And there's a couple ways to go here, okay? If we were going to spend a lot of time on the theory here, I would show you more of a, I guess, a little bit more of a rigorous way to do this, where we use i's, we actually find the nth partial sum, and we take the limit of the nth partial sum. But I'm going to show you that, and all we have to do is list out a few terms, and we'll be able to see what's going to happen here. Okay, so let's just say I start listing these out. But first what I want to do is split this up into two parts. Okay, so I'm going to do it like this. I'm going to say this is equal to, because with summations we can split these up into pieces. So I can say this minus the summation n equals 1 to infinity of 1 over n plus 3. So all we do is we split these apart at the plus or minus sign. Okay, and it's sort of like what we could do with integration, right? This is sort of like a discrete equivalent of an integral, which would be more of a continuous case. So we can split this up just like we do there, and then let's just list out some of these terms, and then list out some of these terms. Okay, so what we'll see is that when I list these terms out, when I plug a 1 in here, I'm going to get 1/3. Then this goes to 2, which gives me 1/4, and then 3, which gives me 1/5. And these are all being added, right? It's the sum. So this first term here, when we start to expand this, we get 1/3 plus 1/4 plus 1/5 plus 1/6, and it keeps on going. And then I'm going to subtract this one here. Now I'm going to plug this in, so I plug in a 1, so I'll get 1/4. Then a 2, which would be 1/5, and a 3 would be 1/6. So I start off with 1/4 plus 1/5 plus 1/6 plus 1/7, and they keep on going. But now when you can see what's going to happen here, all of these, I'm going to subtract all of these. And then if you look and see what's going to be left, 1/4, 1/4, 1/5, 1/5, 1/6, 1/6, 1/7, 1/7. The only thing left is 1/3. And that is actually the answer. The answer to this is 1/3. And this series is called a telescoping series because what happens is these collapse like a telescope. So it's called a telescoping series. You can see them coming. They have this kind of look, and you start using partial fractions. And when you do that, you've got a telescoping series. And the way they're typically done, like I said, it's not quite as rigorous, but it's the way that everybody does these. And you can see what's going to happen. You list these all out, and then they collapse like a telescope. Like think of one of those pirate, I guess, like a telescope with one eyepiece. Maybe they call it a monocular telescope or something like that. Spyglass, but whatever you want to call it. But it's this is a telescoping series because of that. And we know that if we were to add all those together, so if we go back here, if we were to take all of these and add them up to infinity, the sum would be 1/3. Or technically, we can make this as close to 1/3 as we want just by adding enough of these, enough of the parts together. Okay, so that is a telescoping series. And then, let's see, with any series, we have two associated sequences. Okay, two of them. Remember sequence from section 11.1, the first section? So we have with any series, right? With any series, we have two sequences. So one is a sequence. Remember, they're always in these braces. The sequence a sub n of its terms. So we could list out the terms of the series as a sequence. And also we have the sequence S sub n of its partial sums. Okay, so we've got two sequences with every series. So as an example, if you look at this one, we've got a series here, right? This is a series, and this just keeps on going. So the sequence of its terms, so a sequence, we just list them out. That would be 1, 2, 3, right? And they just keep on going. So this would be like a sub 1, a sub 2, a sub 3. And then also the sequence of its partial sum. So if I add the first term together, I get 1. If I add the first two terms, I get 3. Add the first 3 terms, I get 6. And you just keep on going, right? So this would be like S sub 1, S sub 2, S sub 3, and so forth. So these are the two associated sequences. These are the two associated sequences to this series here. Okay, and that happens for all of them. Well, let's see. If this series is convergent, then we know two things, right? We know one thing. We know that the limit as n approaches infinity of a sub n is going to be 0. We also know the limit as n approaches infinity of S sub n equals S, where S is the sum of the series. And we're going to find out that this would be really nice, but usually this S sub n is impossible or very difficult to find. So we can't really rely on this too much. Just a few special cases. Okay, so summary of the technique so far for determining convergence or divergence of a series. Okay, so what we've got so far, 11.2 is a pretty big section. Okay, so what we've got so far We could check to see if the series is geometric. If so, find the value of r. So basically, if the absolute value of r is less than 1, the series converges. And its sum is a over 1 minus r. Okay, if the absolute value of r is greater than or equal to 1, then the series diverges. And we, of course, can't find its sum. Okay, so we could see if it's geometric. Okay, we could do that. And then we could use a test for divergence, right? Check to see if the limit of a sub n does not exist or it's not equal to 0. If so, the series diverges. And that is by the test that goes by many names. Probably the most common one would be the divergence test. And remember, the unfortunate part of this test is that if this limit is equal to 0, the test gives us no information, so we need a different test. So divergence test, test for divergence, or the nth term test, all the same. Okay, we could also form a sequence of partial sums for the series and determine if its limit exists. So we take the limit of the partial sums, and if we get a number, right, s, an element of the real number system, some real number, then the limit exists. Or if the limit exists, then the series converges, and the sum of the series equals this s right there, right? The sum of the series equals the limit of its sequence of partial sums. Okay? And then finally, we can check to see if the series is a telescoping series. If so, use partial fraction decomposition. All right. I know you're going to be shocked to hear it, but 11.2 is finally over. That covers everything in that big old section. So take a look at the homework, give it a try, and of course, let me know if you have any questions.